Bernard, so, Professor Vossen from Amsterdam. He's not really computational linguist, I would say. So you better you introduce yourself. Vossen is working with the WordNet. The one I know, very active in WordNet with the Christian Philbon.
Yes.
So they are also now, they won some years ago a project called Kyoto.
Yes.
Correctly? Kyoto. Yeah. Without environment or individual sharing technologies or on the environment. So we'll be presenting this project to us and how we can collaborate. So Professor Vossen and the University of Amsterdam, or the University of Amsterdam, is associate partner in our project. So before I give you the microphone, I would like also to introduce to you the two in this room. So I have Professor Christoph from University of Savoy and the University of Lisbon.
I met teacher.
You met
3 weeks ago.
Okay. Oh, yes. Okay, good. And Professor Ruth Costa from New University, Lisbon. She's a linguist. She's only linguist here. So some of us really consider themselves linguists also.
Also a linguist, actually. So.
Background is not IT?
No, I started as a linguist.
So Professor Paolo Bouquet from University of Trento in Italy. Well, he's a philosopher.
So
he was a philosopher, but he now in the semantic web community since many years. And he's the faculty of economics now. He developed something very interesting to linguists, which is entity server. He will contribute in the project also. And we have Matthew Balmenari, Professor Matthew Balmenari from University of Milano Bicocca. He login is database. I can semantic web. A bit semantic web. I was not semantic web, semantic technology. No. And Professor Carlo Tini from also University of Milano Bicocca, originally the database and also but semantic technology.
Okay.
Professor Jamil Harb from the chemistry department, biology department here at Pierce University. He's coming to our meeting, because we need somebody to about the ecology and environment domain and these kind of things. So he will be also with us from Birzet side. Myself, Mustafa technology guy, web ontology, and I think this Arabic ontology, which is you can certain way see it as Arabic WordNet also.
Okay.
My team, there is Anton, the guy who was communicating with you.
Yes.
We have Ruba Isa and Hassan Salami, Ali Salhi. He is a natural language processing guy here. And the communicating Majhab and Dima are also our team. There is also my colleague, Professor Adnan Yahya, but here he is actually the Vice President for Academic Affairs, so he's capacity, so he's very busy. He can go during the meeting. So I'll give you.
That's a lot. A long list of names and people.
So please go.
Okay. Yeah. So I understand I have about 20 minutes for the presentation. So Yeah, it was to me not very clear what would be of interest to you. So I have a pretty long presentation, and I'm going to skip things, or you just tell me, explain more on this, or just go on, or whatever. Yes?
Okay.
Okay, so the Kyoto project was funded by the European Union, seventh framework project, but also by Taiwan and Japanese through national grants. And the goal is to develop an open and free platform for knowledge sharing across languages and cultures. On the one, there is a kind of a wiki environment where people in a particular domain, they can maintain their knowledge by creating terminology, learning terminology, and linking them across languages. But we don't want to let them start from scratch. We actually give them automatically acquired terminology and concepts that we learn from the text in they produce in the field. And some amount of knowledge is built up or available. We use the domain knowledge to do open text mining, and with open text mining we mean to extract facts from the document. So a distinction between learning concepts and use concepts to learn facts. A fact is about the instance, and it is instances in a particular relation to each other, at a particular place and a particular moment in time. That is what for us defines a fact. We collect millions of facts from documents, we put them in a structured database, and then provide some kind of a semantic search on those facts. So the project, we worked on the languages English, Dutch, Italian, Spanish, Basque, Chinese, and Japanese. Of course, to show that we can extract facts in an interoperable way from a semantic point of view across these languages. Where we not only need to do a similar structural analysis of the language, but specifically a uniform semantic interpretation of the language. The plane is the environment. That the system and platform can be applied to any domain in principle. The project lasted 3 years, ended in March 2011. Of about 360 person-months of work, 6 countries, 6 research institutes, 2 companies, and 2 NGOs. Background information, so we now go a little bit deeper. So I think it makes Kyoto different from other text mining approaches. First of all, it's a very generic and open system, so it's not a system specifically defined to extract particular types of information, knowledge, or facts. You can, in principle, apply it immediately to any domain, but then also, if you want to, tune it to a particular domain. So one thing which I already mentioned is that the information and knowledge extraction has to be done in a uniform way across different languages, and in a sense also across different cultures. So it should be able to model cultural and linguistic differences, the way knowledge and information is expressed. Very interesting that we built a complete system, which where we have on the one hand formal ontologies and word nets and domain background vocabularies, but just or collecting these and linking them, we are actually applying them immediately to text mining. And we think text mining is a very good occasion to show the potential of the semantics in an ontology and a link to the ontology word nets. Another aspect is the anchoring of the knowledge be done by the people that are experts in the domain, so the environmentalists in our case, not by knowledge engineers. And that's where the wiki environment of Kyoto comes in. And since creating words is difficult, creating ontologies is even more difficult, and mapping a word net to an ontology is also very difficult. So it was really a challenge how to do this. I can't really say that we. I think we did on first steps on this. So it is easier to do this than using, for instance, Protégé. but it's still more difficult than entering information in something like Wikipedia or any kind of other wiki system. So somewhere in between, and I think it is very easy to use for people from the environment at the moment. Well, it was that if they put effort in modeling their domain, then in return they would get better facts. So that would be the kind of incentive for them to do this. So, okay, I'll skip this. So this picture is a kind of overview of the architecture of the system with the different modules. You had, you can see my mouse, I assume. Okay. No? Yeah. Okay. In the left top corner is kind of a wiki platform where the environmentalists build thematic collections of information, put documents, have links to projects. In fact, what we do is we just capture all the documents and information that provide on this wiki, semantic wiki environment, and we process through what we call the Kyoto core module. So the Kyoto core module will produce some kind of XML, and XML is actually a representation that we developed in the project, which is we Kyoto annotation format, or CAF. The CAF plays a very important role in the project because a uniform representation, which is the same for all the 7 languages that we have. Only that, and I'll explain in more detail, it's designed in such a way that each piece of linguistic analysis or semantic analysis is presented in a separate layer. So it's very easy to develop a program that your representation in the Kyoto annotation format does processing or analysis and adds another layer of information. So in that sense, the system is very open because you can easily extend it to add more and more semantic interpretation to a textual document. And this in more detail later. So every document that the environmentalists just upload in their wiki environment processed to us, and we create databases with CAF representations of the text. And when we have a CAF representation with a basic structure or semantic interpretation of a text, we extract concepts. For instance, red patch infection would be a concept or term. These concepts are added to the Kyoto knowledge base. So it is done fully automatically. The concepts are actually integrated with vocabulary that is already there, which includes word nets for the different languages and also an ontology. So there is something that we call the Wikioto knowledge editor, and that is very easy to use. That's why I have here a baby working on a computer. Easy to use system through environmentalists should be able to pick the important concept to learn. So they mention this is an important concept, that is an important concept, and they can modify the way the information is integrated into the full knowledge platform. In this, they indirectly build a model for the domain. So a group of people can do this for a while, extending the generic knowledge with domain knowledge, and at any point you can decide to use the integrated knowledge representation to the next step, and that is go to back to a collection of documents represented in the Kyoto annotation format and extract facts. So a fact would be, for instance, an event, an infection, which is causing another phenomenon, red patches. It's done to skipper frogs. It took place in Sri Lanka, and the year where this event was reported was 2001. So you generate millions of these structured pieces of event information for the documents, put it in a database, and then provide some kind of semantic search. Okay, that's the overview. So now turn to the Kyoto annotation format, which is actually the central part of the project. the annotation format is, as I said, it's a layered representation. It's based on the layered annotation format proposal in the ISO group by Nancy Ide and Laurent Romery in 2002, called LAF, and that is been represented by the proposal for graph, which is a follow-up. It's a standard annotation, so not an inline annotation, which means that somewhere at the bottom you have a original document, which could be a PDF, or maybe it's another representation of the text. From you will extract the textual elements, and you keep track of the offsets, the positions of where the text was found. So if you have a scan, an image of an old encrypted text, you can keep that intact and just point to the positions where you found the characters or the symbols that you're representing. So out of this layer, you build another layer which we call terms, and the terms is an interpretation of the text tokens into words or expressions. You represent that separately, and you point to the previous layer to indicate which elements from the text make up a term. And so you go on, you build up chunks, and the only thing you do is you point to the terms that make up a chunk. You specify dependency regions, you only indicate which chunks or which terms are related through a particular dependency. And so you go on building new layers without affecting the structure of a previous layer, also keeping the others very simple and easy to process, because each layer just contains a simple piece of information. Actually build parallel structures where one program will represent the text into terms, which other program that does the same thing and just adds another term layer as an alternative interpretation, and you can combine these. So potentially this is a very powerful way of representing an analysis of linguistic or textual information. So through this is the same for the 7 languages that we have, and because it's the same, we can actually share a lot of the semantic modules for the different languages. So one piece of software that is doing multi-word tagging for English, for Spanish, Italian, Chinese, Japanese, Chinese and Dutch. You rather need to split compounds that instead of detecting multi-words, so that's another module. We have other for word sense distinguishing, and it works the same for all the 7 languages. The only thing it needs is a structure taken from a word net. We have exactly the same. The entity recognition is one module. Ontological tagging, so we are inserting semantic layers with ontological classes into the representation. It's the same for all the languages. And searching through the output of this is exactly the same. And this is important because we want to have a uniform semantic processing of the text, so that the information you extract across the different languages is interoperable. All right, I get a bit through the examples of I don't have time to go into details for everything. So this is a presentation of the textual layer. You have identifiers for word tokens, so W1, W2, W3. You indicate which page, which sentence, which paragraph. You indicate the offsets where you found the actual word, and then you have the words themselves. So here you have large migratory birds. Next would be the term layer. So here's the text layer again. And here you see the term layer. It's a separate layer in CAF. And again, unique identifiers for terms, term 1, term 2. And you can see here this term has a span. It points to the first token. And this one actually has a span consisting of 2 word tokens, because migratory bird is recognized here as one multi-word unit, and therefore it's one term but refers to 2 tokens. You also see part of speech information. This is a noun, this is an adjective, it's an open class word, etc. So in case of chunks, the only thing that we do is you add a new layer, very simple. We give an identifier, we say which term, the second term in this representation is the head, the first is a noun phrase, and again we give a span of all the terms that make up the constituent, this chunk. So you have this joined terms to be the same chunk. The is also very simple. You have a dependency between term 1 and term 2, and there's a modifier relation. So you add up the different layers. When we add semantics, we actually do it a little bit different. So at the term layer, we insert references to an external resource that you see here, for instance. So here you have the term population, it's a noun, and it points back to the fourth word token in the text, and references to external semantic resources. So here we pointed to WordNet 1.7 with the synset identifier, and this is a confidence score where word sense disambiguation assigned the score to this synset, and it's actually scoring all the different meanings of population with the confidence score. We can insert ontological references. So we point to a Dolce class and we say, well, this is actually, according to Dolce, it's a group and it has a confidence of 80%. Okay. Well, so far we just represent the text as a sequence, but you can also add different types of layers, like the named entities are represented only once. So this is a named entity representation for location, and the location is the United Kingdom. We found occurrences of references to this location in the text. We found here on the second page, term 453 was a reference to the United Kingdom. And on page 7, we found another reference. So we send the entity only once. We take information from GU names, and we point to all the occurrences in the text where there was a reference to this named entity. Named entity recognition, we follow a procedure where we first determine what are the main countries of a document, and then try to interpret every city, place, river, mountain, or area within that country and priority within the country. So to avoid the ambiguity, because almost every place in Europe is also a place in the United States, for instance. See that we have a kind of a link not only to GUnits, but that name is also linked to WordNet. So here you see a WordNet identifier, a hypernym of WordNet, so that we know what kind of place it is. And actually, that WordNet synset is linked to an ontology where we say that in what it is in the ontology. In this case, it is an island in the ontology. So we know the United Kingdom is an island. So, so this was the Kyoto annotation format. So the step will be extracting concepts from that. Oh, sorry. So this is just the format itself, but the format, there's also another system behind it. To say a bit about that, so we have a kind of a document base where you can build up a database with CAF representations for a set of documents. So it's a simple database management system where you can put in as many CAF representations of documents as you want. When you database, you can link to the database with a so-called pipeline of modules that you will apply to CAF to enrich it with new layers or new information. So pipeline you can create through a module that we call Pipette. And Pipette, you can actually create a pipeline out of any series of applications you want. So until we have a set of modules which are developed by different partners in the project. So there is a module that converts PDF to HTML. So it has PDF as input and produces HTML as output. There is a module that reads HTML, sends it to a parser, a server somewhere, gets the server back and converts the output of the server in the first representation of CAF. Then there is a module, the multi-word tagger, that will read CAF and produce CAF but detects multi-words. And tagger that will read terms and sentences or synsets from WordNet into the CAF and produce CAF. There is a named entity tag that reads CAF and produces CAF. There's an ontological tag that reads CAF, produces CAF, etc. There is also a program called a T-bot, a term-yielding robot that reads carves and detects terms and puts the terms in a term database. A program is a knowledge-yielding robot that reads carves and generates facts. You can make your own modules. You replace existing modules by new ones, whatever you want, very easily. And then you can create a pipeline by making a combination of those. So here, for this database, you see there's a pipeline associated with the database. It'll do PDF to XML conversion. It sends the output to an English parser, which is a server somewhere else. Then multi-word tagging, sense tagging, name identity tagging, onto tagging, and then the T-bot finally creates a database of terms. So pipeline is associated with this database. Then there's a job dispatcher that will check for every document in the database continuously what is the next step in the pipeline that needs to be applied. So you can, in multiple threads, you can define every module how many threads it should run. So it could be that the system is actually doing, for one document it's doing multi-word tagging, and another one is doing for 5 different documents it's doing named entity tagging at the same time. So you can organize that yourself and run that through the job dispatcher. You can also associate with different databases, different pipelines doing different processes. Okay. For the concept extraction, this is what we said, T-bot, or the term yielding robot. So it operates on CAF. It operates exactly the same way in any language. So we did it also for Chinese and Japanese and for Dutch and for English, Spanish, Italian. The only thing is that it needs a very simple pattern. It needs to know which part of speech or chunks it needs to operate on. It also needs to know a pattern to know where the position is of the head of a phrase. Using just a representation of the terms. So you need the text layer, the term layer, and chunks. You can do it after you've done word sense disinformation. That means that every term has a mapping to syntax with a score. And that's that you're not only extracting terms, but you're linking these terms to an existing word net integrated with the generic knowledge. So module, I mean, in principle, it's not using anything new. It's just doing a basic term extraction. So using a morphous syntactic analysis, it will know that a terrestrial species is a sequence that can be a potential term and it will be linked to species. It will also use pattern-based analysis. So if you come across things like amphibious species such as frogs, then you know that this is so. The frog is also a type of species. A distributional statistics. So you can use information that both soup and sandwich are object of eat. Merge concepts through WordNet. So we know that lime tree, linden tree, basswood are actually, if you come across those in a document, they are not separate terms. There are synonyms of the same concept. And through the WordNet linking, we can actually link terms already across different languages. Example of a screen of a program that we have to visualize terms that we learn. I'm not sure if you can read it very well, but in the center here you have the concept tree. You see all the brownish boxes, which are all kinds of like bang trees and acacia trees and mature trees, which are terms learned from the environmental documents which are not in WordNet, which are not detected in WordNet. You also see blue ones, like here you see guava at the left top corner, or a citrus, a pecan tree, a tamarind, or here a logwood tree. Blue are terms that occur in the document that are also in WordNet. We found the proper WordNet, and that meaning linked it as the hyponym of tree. So you see a mixture of new terms and known terms. Actually, sometimes you have tree, and here you have a willow tree, which is also a good WordNet, and below you have black willow, growing willow, creeping willow, vicious willow, downy willow, shining willow. I have if these are types of willows or are just willows in certain conditions. That's something that a biologist or environmentalist can decide, not our program at this stage. So, but see that WordNet provides you a more fine-grained structuring of the terminology that you acquire. And we use that as a starting point for environmentalists to decide what are really proper terms and what is the status of the term. You'll see sometimes a red note. This term didn't occur in the document, but WordNet, and it actually groups a whole batch of. Let me see. Is there an example here? Nothing. Yeah, here, for instance, you have pine and pine tree. So pine tree is not occurring in the documents, but there are terms in the documents that link to this one in WordNet, and that one connects it to the rest of the whole hierarchy. Actually, introducing in this network nodes which do not occur in the document, but provide a better structuring according to WordNet of the full terminology. Okay, I'll go on. So I move a little bit to the knowledge structure. I will not talk about the knowledge editor. So how to find all the knowledge that is available, because you have something like DBpedia, which has 2.6 million things represented, geonames, 8 million geographical names. There is species 2 database, which has 2.1 million species in there. We have WordNet with 50,000 to 120,000 synsets. We have a lot of different ontologies, and we learn a lot of new terms in our term database. And all of that needs to be integrated in one knowledge model. So we cannot put everything into the ontology. It will be way too big. There is no inferencing system that can handle that amount of information. It's crash. It is also very diverse. It's not, you don't have everything in the ontology. It's a different knowledge that you find in the terminology than the kind of things that people usually put in ontologies. And the types of knowledge require different types of inferencing capabilities. So what we did is we used a model from Putnam, the philosopher Putnam, which is called the division of labor. And in the model, we copy to let's say semantic web situation. So according to Putnam, people can use the term gold even though they cannot distinguish gold from other material, and they rely on the fact that there are experts around that can do that. I use that same idea, but now we say, okay, we only put the real knowledge for the computer in the ontology, but the computer doesn't need to distinguish between two strict types of frogs in the environment, because we can assume that if we tell the computer these are different types, then there are specialists that confirm that and they know how to distinguish one frog from the other frog. The only thing that we put in the ontology is the information that the computer needs to know to detect facts in the text. So not all the knowledge to do inferencing is in the ontologies. A lot of knowledge will be kept outside the ontology, and the computer can assume that these are just different types of things. Different kinds of inferencing on different knowledge repositories. So I skip a little bit. So what we have here is we have an ontology in Kyoto, which has about 2,000 classes and 3,000 axioms, and it's an extension of the Dolce ontology. We have WordNet, which has about 100,000 concepts. We have 8 million places and geonames. We have, for instance, up to 3 million species and species 2,000. So what we do is we define a mapping for all the important basic concepts in WordNet. Anything that is linked on top of that. These are mapped to endurance, qualities, permanence in our ontologies. We have a few domain concepts which refer to specific processes which are important in the environment domain. And through the base concepts, all the nouns, all the verbs, all the adjectives in WordNet are linked to the ontology, either directly, indirectly, through the hypernymed relations. And by default, we assume that everything that is a hypernym of something else is a disjunct type of thing. That's the default relation. I build up a domain word net from the terminology that we learn. For instance, the environmentalist in our project built a domain word net for 1,200 synsets. 210 of those occurred already in WordNet, and 1,000 of them were new, and they created 990 mappings to the ontologies. The greenhouse gas is something which is already in WordNet. Not only we know what kind of thing it is, that is a substance, but we all know that it plays a particular role in a pollution process. See, this defines greenhouse gas not as a type of gas, but it defines gas playing a particular kind of role. And that's the only information that we want to know. Also, like polluted water, for instance, is not a type of water. It is water which plays a particular role in a pollution process. Okay, we have mappings of the G names to WordNet, so we know what kind of places are, and to all 3 million species are linked through 150,000 mappings to WordNet hierarchy, which is indirectly mapping them to the ontology. This model can be used for ACE, but also for all the WordNets that have equivalent relations to English can indirectly be mapped to the same system in this model. Quit bit here. So, in principle, the situation follows. Suppose you come across this term here, I'm not even going to pronounce it, the Eleutherodactylus atrabrachus, the thing here at the bottom. You come across that thing in a text. I don't know what it is, but we find it through a Sparta query in a source database with 2.1 million species. Okay, this thing is not linked to WordNet, but it's linked to that class, and we go up the hierarchy through Sparkle. And then suddenly, if we find in there a concept which is to this one, WordNet, we go WordNet and we find the base concept, and now we know that it is an organism. Actually, we know more because there's not special said about the concept. Simply assume that every branching that we find here, every branching that we find there, is distinguishing this concept as a disjoint concept from all the other ones. So we know that whatever thing we find here, it is disjoint from another thing that we find there. They cannot overlap. So we find a term which is actually directly mapped, but then we go with the same thing. We know for all of them that there are some type of organism. Some type of organism doesn't overlap with another one. Different terms are learned from the documents. If you look at the environment documents, you find things like endemic frogs, endangered frog, poisonous frogs, alien frogs. And a frog is not a type of frog. Frog is alien because it is in a particular circumstances. So into frog, but through mapping we want to define that this is not a frog, it's frog which is involved in a particular process. And that is important information because we want to find information about instances which are involved in particular processes that take place at a moment in time and at a location on the Earth. You want to know facts about these instances, these little friends over here, and the way you can refer to them through their name, but also through all kinds of other ways. Okay, we have that knowledge. The next step is actually extracting facts. So sentences like this one: tropical terrestrial species populations decline by 55%.
Can I ask you, please?
Yeah.
So just to follow you, because you are not in front of us. I mean, personally understood.
Yes.
Not in front of us. So say face by face, before saying facts. I mean, there's other questions or inquiries from the audience.
Yeah, sure, no problem. You have to stop me. I mean, I just go on until you.
Anyone has a question?
No, I have just my question on one of the issues you described, which is the annotation entities there.
Yes.
You were trying to link the entity with, for example, with the field names and identifiers. Okay. For example, how do you do that? What kind of techniques for finding the matching in names, and what you do for entities which don't have an established identifier in any resource of the web.
Okay, so in the case of the G names, you can see there are here 663 mappings. What we did is that in the G names database there is a label what kind of location it is. So we linked those labels to the proper WordNet syntax, and we did that by hand. That was easy. There were only 663. So that the UK is an island because it has the geonames property of being an island, and something else is a mountain range, and something else is a city. So that we map individual locations to WordNet, but only map those types. For the species 2000 is a different story.
For example, if UK and United Kingdom in another place, they are the same entities. For example, you have UK.
Yes.
You have United Kingdom.
Yes.
Or have Great Britain, or maybe in Japan is written some. I mean, do you think entities? This entity is the same as this entity, is the same as this entity?
No, in the GNA database there are a lot of variants already. So that there is a lot of that already available. And for the rest, there is the way we go through the text. We do string matching to find we look at a lot of different features to figure out if this may be a named entity or not. And there is also a difference because we don't need to detect a reference to a named entity in occurrence in the text, as long as we know sufficient references to deduct the actual location where the fact took place. That's not the same thing. So if we find good evidence that things happening here in the UK, evidence for other locations, that is assumed that the things happened in the UK. That means that every fact that we extract, we actually go through a particular procedure. If we extract a fact, we first look in a sentence, very good evidence about the location of this fact in the sentence. No, then we go to JSON sentences. No, then we go to the most evident location that we have in the whole document. We look at the not only at the frequency, but also at the relations between, for instance, the country and the places within the country that we find in the document. And if there is not a very clear dominant location, then we go to the beginning of the document and take the first one that is with the high confidence that is mentioned in the text. So they're the fallback mechanisms that we use to determine the location of an event. Not 100%. But we don't need to detect perfectly every instance of a location.
You have
Martin? Yes, sorry. I have one question. When you have all these different kind of knowledge, do you assume to have one-to-one mappings between the elements of in each sources, or end-to-end mappings? And because this is related to, if I understood correctly, you say that you assume that the disjoint syntax in WordNet are interpreted as disjoint concepts in an ontology. Is that right? Okay, so
it's the default. That is the default. Yes.
This is a default. So I assume that if this is the default, you can break this rule and, for example, map two different sets to a same concept in an ontology, or not.
I mean, a lot of the mappings to the ontologies, so different types of mapping relations. We have a whole range of mapping relations from a concept to the ontology. So the map of either or a synset in WordNet or something in the terminology database to the ontology can be pretty complex. But in the basic case, so in the case that what I showed here, if something very specific and you just go up the hierarchy, and you end up with there is always a subclass relation in a class as formally defined in OWL. It means that animal is a subclass of organism. This is a subclass of animal. This is a subclass of chordate. That is a subclass of vertebrate. This is an equivalent relation, and again a subclass relation.
So in this slide, so this SOX database is the database about animals and so on? Or?
Yeah, this is the Species 2000 database, which is there. That is a merge of something like, I think, 5 or 10 initiatives in the world where they build databases of species by biologists and environmentalists, and they combined all of them in one single database. And I think the numbers, sometimes they say it's 2.1 million, sometimes they say there are 3 million species.
So actually in Kyoto, not only that you have documents, but you are really linking to databases, right?
Yeah, so this is the knowledge base that we build up, which we call these are concepts that we have to deal with, and the vocabulary is linked to the concepts.
So you mapped the 2.1 million records.
Yeah. Yeah, so that's the other thing here. So the 50,000 mappings from the species to WordNet. This was created automatically by a program developed by the Basque University, where they used a square to align two hierarchies. Take the hierarchical structure of WordNet into consideration. They take the hierarchical structure of Species 2000 into consideration, and they try to harmonize the two hierarchies as much as possible. And that is 150,000 mappings.
And now you take, for example, a PDF file or a Word file, and if you frame of an animal, you map it to the database.
Yeah.
And because the database is mapped to WordNet, and WordNet is mapped to Dochi,
yeah.
So you get the whole mapping.
Yes. If you come across this term in the text, so that this is one term, but also know what kind of thing it is according to your ontology. So derive through the relation that this is some kind of a subclass of an organism. We don't represent 2.1 million species hierarchy in the ontology itself.
Yeah, the species will be in just another database, and you just map them.
Yes, yes.
They should be in the WordNet. Well, let me ask this question. They are not. Why, let's say, theoretically speaking, we don't have all of these data in the WordNet or in an ontology? I mean, they're not really instances. They are concepts.
They are all concepts, because in the text they can talking about 10 of these green things, and these 10 are instances. They also talk generically about them, then I don't refer to any instance, they refer to the concept. So we know what the instances are at this point. These are all concepts, that's true, yeah. Now,
but these are terminology in the language.
Yes.
They are types of this animal, which means they are not instances, they are concepts.
Yes, exactly.
They have words in the language. So
I mean that they are instances. So our knowledge structure, these are all concepts. The only instances that we have are the geonames, the cities and the countries. They're instances. These instances, they're all concepts. Everything on this slide are concepts.
And sorry, so back because of course this example is a good example of hyponymies that kind of satisfy the subclass semantics. This, of course, in WordNet is not always the case. So since it's very interesting, the also amount of mapping you created. Wondering if you came up with some statistics about how many times these lead to wrong mappings between word and ontologies, or if you ever like kind of encountered this problem.
The mappings for the so explained in this picture about 1,000 base concepts to our ontology here manually.
Okay.
Completely manually.
Okay. So in this case, you are sure that you made the mappings in accordance. Okay.
So the only thing where we can be wrong is assumption there is a hyponymy relation with the other concepts in WordNet to one of those. Our default assumption is that it is a different type of thing, and that is not always true, because we use the Dolce distinction between rigid and non-rigid concepts, and we have a program. Probably Christiana told you about that, which is called the Rudify program, which automatically tries to make a distinction between base concepts that are rigid and concepts that are not rigid. So a rigid concept is, for instance, a dog versus a cat. Those two are rigid because you are born as a cat and the cat will never become a dog. And rigid concept is the concept of a pet, because cat can become a pet and then she run away and then she's no longer my pet. So the pet is a non-rigid concept.
Yeah, but this is not a problem only of rigidity or not rigidity. Like in WordNet, you can find hyperonymies that connect together concepts that refers to individuals that are really different. Like, I have an example because we're just working at an algorithm.
Yes.
Matching ontology using WordNet. Like, for example, if you look among the hyponyms of, if you want to map, I should pick up the email, but if you want to map actor with person, there are like some synset of actors that links to groups. So you even like sometimes in WordNet you have relationships that are basically part of relationships or something like that, right? So yeah.
Well, I think this is another issue. Just to move faster. Is there other questions?
Just perhaps to help it to complete. So if on the side, to precise, the Kyoto ontology is automatically extracted text. Is that it?
Automatically
The ontology is automatically extracted.
I mean, data here is what we call the ontology. So the 2,000 classes and 3,000 axioms is an extension of Dolce Light and onto WordNet. That's all built manually by the group of Christiane Feldbaum in Berlin. This is all built manually. The things of the base concepts to the ontology is done manually.
So
here, the main WordNet is built manually out of the 500,000 terms that we learned from the environment documents. The little terms and the map of the terms to WordNet was done automatically. But the environmentalists started working on the main concepts there and picking out, selecting, and slightly modifying them, anchor these new ones to the ones that were already in WordNet. And then manually.
If we want to extend Arabic, what exactly we need to do?
So if you want to follow this approach, the fastest way to do it is what we did with the other languages. So for instance, for with this framework built up here, and this is full with English examples, but actually names and species 2000, and we also use DBpedia. You all have the concepts in Arabic and the other languages. So what we did here for Dutch is, the only thing that we did is we ensured that we map every synset in a Dutch WordNet to these base concepts over here. Sometimes directly by finding the equivalent, and sometimes through the hyponymy relations that we have in a Dutch WordNet as well. It means that the whole Dutch WordNet is anchored to the same ontology. Anything else, I don't really care where it comes from GU names or species 2000 or DBpedia, through English labels, Arabic labels, or Dutch labels. I don't really care, because I will go up somewhere to this network and find a match that matches to the ontology. It can come from here, it can come from my Dutch WordNet, it can come from an Arabic WordNet.
So Arabic WordNet, and then we map it to its one set base concepts in WordNet.
Yes, exactly, and then you can use the same framework.
I see. So is it clear, guys? Here you can follow about open source and availability of the code.
Yeah, all the code that we developed is open source and available. You can directly download it. And the only thing I have to say, it's not so easy to get. The documentation is poor, very poor, and it's pretty complicated. But I think you just ask, and everybody is willing to help. I think it's a big project and pretty complicated, and we just had no time to really deliver the thing.
I have a question.
Okay.
You mentioned a reasoning that each type of
yeah.
type has different instances. So when you mentioned about reasoning over ontologies, with did you refer to reasoning about the scheme of the ontology, the T-box, or reasoning about the individuals, extracted them from the fact?
Yeah.
Sorry, before, because I would like to add something to this question, actually. So it's strange for me that I see that you actually consider formal reasoning in this project. It's much better just to have the reasoning as just a search engine, bilingual search engine.
Ooh, this is each separate question is already complex, and to put them together is even more complex. Let me make a start. I mean, this referred to actually the fact that different types of knowledge and different volumes of knowledge may require a different engine or a different method of getting properties. Sometimes it's easier or more efficient to use Parquet queries, and some you want to do formal reasoning. Actually using in the project is, yes, we do use Parquet queries on this cost database of species. We use the graph algorithm to do word sense disambiguation, actually. For formal reasoning, we tried a number of things. In the end, we did it differently. We not do inferencing of instances in the actual text, so we do try to represent classical formal representation, logical representation of the sentence, quantification and everything in that. That is, I think, too complex for the kind of thing that we want to achieve. what to do, and if there is time left, I can show maybe a little bit because it is in the rest of the presentation. It's first what we call offline reasoning on ontology, and that we expand every concept in the ontology with the set of all the implications that are modeled in the ontology to subcollaborations and axioms, etc. So this the whole Dolce ontology and our extension into the full set of all the implications that apply to every concept in or class in the ontology. So because we think, and actually we made a particular selection because not all the implications that are modeled in Dolce were interesting for us. So we made a selection of the things that were interesting for us. The kind of reasoning that we do, we put that full set of implications into our representation of the text. And we use, am I still connected?